Before you watch this video, please be advised that this is not an original recording. The recording of the audio is identical, but the screenshots have been captured from an actual presentation. Therefore, some of the animations that would normally be present in the video are not present. To compensate for that, we have included a link to the original presentation document that you can view alongside this webinar. Enjoy.
Hi everyone, my name is Michael Snoyman. I would like to introduce you all to Denny Bertovich, who will be giving a talk today about deploying applications to Kubernetes. I will let Denny take it away.
Thank you, Michael. Hi everyone, my name is Denny. I'm a software engineer at FP Complete. I'd like to say that we at FP Complete, myself included, care a lot about Haskell and DevOps, and hopefully I can show you today how to bridge the gap between the two and how to leverage modern DevOps technologies that will let your development team be more efficient and independent. Okay, so let's start by talking briefly about what we'll be going over in this webinar. So we're going to start off with a Kubernetes intro. So we're going to define what Kubernetes is. We're going to talk a little bit about what that means and what features Kubernetes supports. After that, we're going to be showing an example of how to create a Kubernetes cluster using Terraform and Kops. We at FP Complete love Terraform very much, and we use Kops a lot, and it has proved very efficient for us. We also use AWS a lot, and while the example here is showcasing AWS, because we've had a lot of experience with that. The following examples after we've created a cluster should be transferable to any other cloud platform or hosted Kubernetes offering. So the things you learn today, you should be able to use in your cluster as well. After we've created a cluster, we're going to describe various Kubernetes terms. So we're going to talk a little bit about pods, what those are. We're going to talk about deployments and how they relate to services and some other terms as well. Once we've defined those, we're going to start building a Docker image for a very simple YesOd application. And we're going to try and deploy that Docker image to our newly created cluster. At the end, we're going to talk a little bit about Helm, what that is, how it's going to help us with CI/CD, continuous integration and continuous delivery, and we're going to showcase some useful Helm charts or components that we use in our clusters. All right, so let's get started. So what is Kubernetes? So from their official website, it says that Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. Emphasis should be on containerized, obviously. But in essence, Kubernetes is basically a scheduler. Deep down, the core features are that of a scheduler with a lot of other features on top. So what is a scheduler? So a scheduler abstracts over a cluster of machines. So those can be VMs, bare metal, etc., and provides a common language for deploying those, deploying your applications to those machines, bearing in mind certain resource constraints. So that means that if your application requires a certain amount of memory or CPU, the scheduler is the one that's going to take care of putting those applications on the correct nodes that have those resources available, and is going to keep track to not over provision nodes with certain applications so that those resources are depleted. So in essence, this is what Kubernetes does, right? So a lot of features that Kubernetes supports is, again, this is from the official documentation. It supports automatic bin packing, which means, just as I've described previously, it supports packing your applications on the nodes in the cluster, bearing in mind the resource constraints. It is self-healing, meaning that in today's cloud infrastructure, a lot can happen in the sense that a node can die, but the scheduler, Kubernetes, will take care to move your application from a dying node to a healthy node so that you experience minimal downtime. This all happens automatically. It supports horizontal scaling out of the box, which means that you can scale your application horizontally and have multiple instances of it, and it automatically provides service discovery and load balancing on top of those multiple instances. It also supports things like secrets and configuration management and much more. So let's start off by trying and creating a Kubernetes cluster. So what we do at FP Complete, we use Terraform to create the underlying infrastructure, meaning the virtual private cloud, the VPC, the subnets, and all of these lower level network details in which the cluster is going to live. And then we use Kops to provision the cluster inside of those resources. The reason for that is twofold. So we like Terraform a lot. We like to manage our infrastructure as code. Terraform provides that for us, and we'd like to be able to add additional resources to our existing clusters that may live outside of the cluster itself. So for instance, if we have a VPC that hosts our production cluster, but we may also have other resources in that VPC, for instance, a Postgres RDS database or similar. That's the main reason why we use Terraform for the low-level network resources, and then point Kops to install the cluster inside of those. Although it's worth mentioning that Kops does support creating everything itself, but then it's a little bit more convoluted to tell Terraform to provision resources inside of the VPC that Kops created. So let's get started.
Actually, Denny, if I could ask one question from the audience first.
Yes.
Why do we need service discovery?
So the main reason why we need service discovery is because our application is ephemeral in the sense that it's living in the cloud, but it can move between the nodes that live in that cloud. So we need a way to be notified, if you will, of the application being moved to another node so that we can proxy traffic to that new location. This is especially relevant when we're load balancing between multiple replicas of our application. I hope that answers the question.
I'm not seeing a follow-up. Thank you, Denny.
Okay. So let's go ahead and create a cluster. So at FP Complete, we've created a list of modules called Terraform AWS Foundation. As you'll see later down the slides, we're pretty fond of the word foundation because we use it a lot for some of our base infrastructure. So as we've been working with Kubernetes and Terraform and AWS a lot, we've sort of created a set of reusable modules that we can use between projects that we've published to the Terraform registry. So this is open source and anybody can use it. And what we're going to do is we're going to go ahead and create a VPC in AWS. We're going to specify a VPC CIDR range for that VPC. We're going to give it a name. We're going to give it some metadata, some tags, and apart from that, we're going to create a set of public subnets that the Kubernetes cluster is going to use. We're going to tell those subnets to live in the VPC we've created above, and we're going to assign some metadata to those. And once we plan and deploy this Terraform manifest, if you will, these resources are going to be available in our AWS account. And once those resources are there, we can go ahead and use Kops to start the creation of our Kubernetes cluster. So we're going to use Kops, which is a CLI tool, freely available to everybody. And we're going to use the Kops create cluster command to start the initial step of creating our cluster. There's a couple of flags that we set here. We're specifying that we're running in AWS. We're specifying the low-level network driver that we're going to use. We're specifying, and this is especially important, we're specifying the network CIDR that the VPC lives in. We're specifying node count and node size. So if we're having a cluster that requires, let's say, high memory instances, we might use those. But if we're creating a cluster that we anticipate is going to be hosting CPU-intensive applications, we might choose some other instance type. And obviously, we're specifying the VPC ID as well and some other metadata for our cluster. So once we run this command, Kubernetes Kops is going to create a manifest file on S3 in the S3 bucket. And what we're going to have to do is we're going to have to edit that manifest file that lives in S3. So we can do that by running the Kops edit cluster command. This is going to open up our favorite editor. And we're going to have to make sure that the network CIDR and the network ID are consistent with our VPC. And we're also going to have to make sure that the subnets, specifically subnet IDs and CIDRs and zones, are consistent with the ones we created in Terraform in the step before. Once we do this, and we can get this information from the Terraform state, or we can get this information from AWS console. Anyway, once we enter this information, we save the file, it's going to propagate to S3, and we can go ahead and run Kops update cluster, which is going to list a set of steps that Kops is going to perform. And if we examine those steps and are happy with the resources that Kops is going to create, we can go ahead and append --yes to actually apply those changes. So kind of like Terraform, where there is a two-step process for plan and actually applying the changes, Kops sort of supports the same thing with its update command. We're going to have to wait a few minutes for the cluster to actually come up. But once it's up, we can go ahead and run Kops validate cluster, which is going to tell us if the cluster is up and ready to start hosting our applications. So once that's done, we can go ahead and start and deploy our apps. However, before we go on to that, there's a couple of Kubernetes terms that we should be familiar with. The smallest unit that Kubernetes has is a pod. And that's basically a collection of containers that share storage, network, and a specification of how to run those containers. Usually, we never deal directly with pods themselves. However, we do deal with deployments. A deployment is a collection of pods. And a deployment is a declarative way in which we specify how we want our pods to be deployed. And then the cluster takes care to satisfy those requirements. Third item that we need to be familiar with is a service. A service exposes a pod to the world or other pods. So keep in mind that our pods or our applications are sort of ephemeral in the cluster, meaning that a node can die or a pod can be scheduled on a different node each time. We need to be able to somehow expose that pod to the outside world or to other services that depend on it. As you're probably familiar, Docker supports a way to expose ports on the host level. However, this is an abstraction on top of that where the Docker container, hence the pod, can be moved across nodes and we still should be able to communicate with it. All right. So now that we have the basic terms out of the way, and now that we understand what a deployment does and what a service is for, we're going to start building our Haskell Docker image. And we're going to be using a very simple YesOde web application in this example. Actually, it's one of the stack templates for starting a new YesOD application. So that's what we're using to deploy to our cluster. And the end result is going to look like this, which we'll get to in a moment. So,
Denny, we just had a question coming back to the Kubernetes setup itself. Is there a specific reason for using the Flannel networking driver? Can you give a guideline on which is a reasonable default? Kubernetes seems to support a range of networking options.
Yes, so that's a very good question. We've found that the Flannel default is sort of worked best for us. It was the easiest one to manage. And we haven't found any surprises with it. So there isn't really a specific reason why we shouldn't use another networking driver, but we just haven't found any requirements that would force us to switch. Flannel sort of worked best for us at this point. Hopefully that answers the question.
Cool. Thanks, Denny.
So let's go ahead and try and build our Docker image, right? So I've written about this before in a blog post on the official FP Complete blog. So you can probably look a little bit more about different methods of building Haskell Docker images there. But in this specific example, I've chosen to use the Docker multi-stage build. And what this does, it separates so we still have one Docker file, but it separates our build into two phases, if you will. One is the build step, and one is the production image, basically. And the reason this is in the build step, you will have a bloated image, possibly with all of your build requirements, your build tools, and so on, that are required to actually build your application. Whereas in your production image, you don't necessarily have to have those. You kind of have to only have the final artifact that you wish to deploy to production. So here, we are using Stack to build our application, and it's going to save those executables in a certain path, which we'll see down below. And here, the second phase, we're just installing some runtime dependencies, and we're basically copying over the binaries from the previous build step into this image. Now, this is tidy and best practice, but it also keeps our production images very small. If this is not a concern for you, then you can probably get away with building everything in one step. But if your images start bloating and getting larger, and the deploys start taking longer because the image download is taking way too long, this is a good way to solve that problem. So once we have this Docker file, again, this is a standard YesOD application. We're going to go ahead and build the Docker file using the docker build command. And we're going to name the image. This is a fairly long name because we're using our hosted registry on our GitLab instance. And we are going to push that image to our registry. Again, if you're using Docker Hub, you can use that. If you're using any hosted registry on GCP or AWS or Azure, that works fine as well. And to test that image, we're going to run the image. We're going to run the myapp binary, and we're going to expose port 3000. And if we navigate in our browser to localhost 3000, we should see the screenshot that I showed a few slides back. So hopefully this image works. What we're going to do now is we're going to go ahead and try and deploy our image to our newly created cluster. So to do that, we, if you remember, have to create a deployment. So here we're specifying kind equals deployment, and we're giving it some sort of metadata. We're giving it the name. We're giving it some sort of tags or labels. And we're specifying here which containers should run in that pod. We're going to just be running one container. And this is the image that we're going to be running. And this is the port that we're going to be exposing. Apart from that, there's some Kubernetes specific things in here. So first of all, we need to talk about the readiness probe. So once a pod starts, the scheduler Kubernetes needs to be certain that the application is actually working before putting it in the pool with all the rest of the replicas if you're having a highly available setup. So this is the path that it's going to check if and expect a successful response before it puts the pod in rotation. Similarly, it's going to keep checking if the pod is alive, and if it's not, it's going to take it out of rotation. So in this case, if a node dies, for instance, or if there's a issue with the node with one of the pods running on it, hopefully the liveness probe is going to fail, and Kubernetes is going to take that pod out of rotation and is only going to serve traffic. Is only going to serve to the pods that are healthy and running on the cluster. So once we have that, we can go ahead and use kubectl, which is a CLI tool for Kubernetes, and run the apply command and point it to the YAML file that we just saw, and it's going to go ahead and deploy our application. To verify that, we can run kubectl get deployments. We're going to see that our application is indeed deployed. We're going to see what the desired and the current count of the pods is. And even so, we can go ahead and verify that the pod is actually running by running kubectl get pods. And we'll see that the deployment has in fact started one pod and that the state is running. So we have our application running on the cluster, but we can't really access it, right? So what we're going to do is we're going to create a service. So kind service, we're going to give it some metadata, some labels, some tags, and we're going to give it a port 80 to expose to the world and to proxy that port to proxy to the pod on port 3000 that we named HTTP in the deployment spec. And we're going to bind this service to the My App application. So one thing to keep in mind here, and I'll get to that a little bit later, is the type of service that we're creating here. So the type is load balancer. I'm going to get to that in a moment. So let's go ahead and apply our service. So we run the familiar command kubectl apply, and we point to the service YAML file that we just created. And to verify that, we can run the kubectl get service command, and we can see that the service is created, and we can see that we have an external IP for our service. So some of you probably recognize this format for an AWS ELB load balancer, which is precisely what happened. So a service type of type load balancer will create an ELB on AWS. So what we're going to have is a diagram like this, where traffic from our users is going to the ELB load balancer, which is then proxying to our service, which are then proxying to our pods and serving the traffic back. We can use the kubectl describe command to get the full URL of our ELB. So there's a couple of problems with this deployment. So first of all, we've hard-coded everything in our YAML files. There's no way to template a YAML file without doing some sort of a command line bash interpolation and regex replace sort of thing. We haven't actually automated any of this. So we're manually deploying our applications to the cluster, and we would want to automate that in some way. We've also created an ELB for our application, which is not necessarily cheap if we have multiple applications running in our cluster and we want to expose each and every one of those to the world or to each other. This is especially relevant in the age of microservices, where we have a lot of those running on our clusters. Also, we've only exposed our application on HTTP. There is no SSL. And also, there is no custom domain on which we can access our service. We only have the domain that AWS ELB gave us, which is sort of ugly. So let's try and solve these one by one. Let's go ahead and delete our service, which is going to take care of tearing down the AWS ELB as well. We're going to go ahead and delete the deployment, which is going to take care of deleting the pods as well. And we're going to start over from a clean slate. So we're going to introduce Helm. Helm is a package manager for Kubernetes. And that's sort of a fancy term for saying that it basically does templating of your YAML files really well. So we're going to go ahead and create a chart. Helm introduces the concept of charts, which is just a set of YAML files like the ones you just saw with values templated out that can be replaced during deployment. So we're going to go ahead and create a chart with the descriptive name chart. And this is going to go ahead and create a couple of templates files for us and a values file. Let's look at the values file. So a values file basically tells you what the settings for your applications are that you can tweak. So you can tweak the image name, you can obviously tweak the image tag, you can tweak the ports and so on and so forth. And it also creates a deployment for you. So this looks very suspiciously like our deployment file before, except that it has a little bit more metadata and it has all of these values templated out. So if you look here, you'll notice that the image name and image tag is something that it's going to get templated in before deploying to Kubernetes. Same for internal port and so on. Helm doesn't really use a special templating language. This is basically just Go templates with a bunch of helper functions and wrappers for Helm-specific tasks. If you're not familiar with Go templates, the curly braces might remind you of Jinja 2 templates, but it's basically the same thing. It's not too bad. We're going to show a more advanced example in just a few slides. So this is our deployment. Basically does the same thing as our hard-coded one. It's just going to deploy our pods to the cluster. Let's go ahead and see what the service looks like. The service is the same with a touch more metadata added to it, but it basically exposes the same ports that can be templated as our hard-coded service file. Note here that we're also telling the service to which application it belongs, but it also gets templated in during deployment. So to actually deploy our chart, we're going to be using the Helm CLI, and we're going to be running Helm upgrade -- install. The reason we're running that is because we want to be able to do an initial deployment as well as subsequent deploys of our application. So this is the way Helm structures its CLI to accomplish that. So we're giving it a name. We're giving it a directory where the templates are located, which is aptly named chart. We're overriding the values, the default values, with our hard-coded YAML file for production / staging / QA. In our CI environment, there's a variable called CI environment name, which basically tells us which environment we're currently deploying to, and it's going to pick that file based on the file name. However, we don't want to hard-code secrets in there or variables that change during each deploy, specifically the image tag. We're going to be deploying a new tag each time. And we've chosen to use a variable that's available to us in our CI environment, which is CI pipeline ID, which is just an integer number of the pipeline for that specific project. You can go ahead and use a git SHA or anything else that's unique per image. So this is going to do the same thing that we had before, and it's going to deploy our service to the cluster. So let's go ahead and automate that. So the way we automate that is our continuous integration and delivery system is on GitLab. We have a hosted version of GitLab, which out of the box supports a self-hosted version of a Docker registry, which we use to push our images to. So we have two steps here. We have a build step and a deploy step. So in the build step, we're going to go ahead and build our Docker image. So this is just a make command that's going to invoke Docker build and give it the appropriate name and give it the appropriate tag and so on. We like to abstract some of these long commands using make. We're going to go ahead and log into our Docker registry, and we're going to go ahead and push our image to that registry. So the second step in the pipeline is the deploy step. And this is going to invoke the command that you just saw in the previous slide, which is make deploy. Again, it's shorter to write the CI scripts this way if we abstract the commands using make. It also helps when one needs to test out the commands locally. We're also going to specify that this job is only going to be available on the master branch, and we're also going to specify that the job is going to have to be kicked off by a human. It's not going to be automatic. The reason being, we don't have a test step here. If we had a test step, we might enable the automated deployments to production. However, here we have an additional layer of assurance, if you will, where a human needs to go into the GitLab interface and press deploy for this to actually be deployed. The URL listed here is actually available currently, and you can check out that it actually works on our cluster. It's going to have HTTPS and everything. And obviously, we can add more steps for staging, QA, so on and so forth. We can specify, for instance, for staging, that it's only available on the develop branch and so on. So now we've taken care of the templating part and the automation part of our deployment, right? So what's left? So what's left is that we still have an ELB for each and every service, right? And that's bad. So Kubernetes has a thing called INGRESS, and an INGRESS can provide load balancing, SSL termination, and name-based virtual hosting. And you're probably thinking that sounds a lot like Nginx, and that's probably because in the default case, it is Nginx. We can see here that the default chart in Helm is actually Nginx based. So we're going to go ahead and reuse the chart that's already available in the default stable Helm repo called Nginx Ingress, and we're just going to go ahead and deploy that to our cluster. And this is going to go ahead and deploy a Nginx service behind an ELB that's going to proxy requests to our various services. So let's go ahead and look at what the Helm chart looks like if we add an ingress. So if you see here, we're adding a kind ingress. We're adding the usual metadata. We're adding some fancy notations here, and here it starts to get a little bit gnarly, where we're doing for loops and the templating isn't as readable as before. We're adding hosts. We're telling the Nginx on which path to proxy to which service on which port. If you've ever configured a Nginx manually, you're probably familiar with all of these terms, but this is how you would configure those in a ingress setup. Also, at the bottom, we're specifying TLS certificates and so on, but we'll get to those in a minute. So the trade-off here that we see is that this chart is a little bit more complex and a little bit less readable than the ones I showed before. However, the silver lining is that I haven't actually had to change anything in this file. This is all created by Helm create, so this is all templated for me, and the only thing I'm going to have to touch is the values file. So I'm going to tell Helm to enable the ingress. I'm going to tell it which host the application should be published on. I'm going to give it some metadata in terms of SSL certificates and secret stores, and I'm going to go ahead and deploy that. And the way this service architecture looks like now is we have one ELB, we have an ingress, but we can have multiple services listening for requests behind of that ingress. So we've accomplished another point from our problem slide. So let's look at how automated SSL certificates work in this case. So if you noticed, we added an annotation to Ingress here that says TLS ACME equals true. And what this does, this signals to a service running on the cluster called kubectl that listens for new ingresses and ingress updates to fetch a Let's Encrypt certificate for us for this specific subdomain. And it's also in charge for renewing those certificates as time goes on, because as we all know, Let's Encrypt certificates only are valid for like 3 months or something like that. So we get SSL certificates for free for our demo application. We also get automated Route 53 entry, a automated DNS entry for our hostname. And that's another component that lives on our cluster called external DNS. It listens for ingress updates and new ingresses and will automatically talk to Route 53 in our case, but other providers are supported, like Google DNS and so on. There's a bunch of them. And it's going to add or update the DNS entry for us automatically. So this is really convenient because keep in mind, you have a development team that is now able to deploy an application all by themselves with SSL, with a custom domain, all without waiting or asking an ops team to set those up. So how does that actually work? How do you get all of these components deployed to your cluster? So we went ahead and packaged something called FPCO Foundation, which is a Helm chart that sort of aggregates a bunch of other charts into a easily deployable package that you can deploy to your cluster so that you have all of these basic features available from the get-go. So to be able to deploy the Foundation Helm chart, we have to do a little bit of due diligence first. We're going to go ahead and use our Terraform modules to create a IAM role that our external DNS is going to use. So nothing fancy, we're giving it a name, we're telling it which cluster should be able to assume that role, and we're gonna go ahead and apply that. And after that, we're just gonna edit a values file that's specific to our foundation chart and tell it to enable certain services. We're gonna enable kubectl, we're gonna enable external DNS, and we're gonna enable kubectl IAM. I'm gonna talk a little bit more about that in a minute. So setup for kubectl is pretty self-explanatory. We're just setting up an email here. External DNS, we're specifying the version we want. And here, notice that we're specifying the IAM role that's going to give this pod permission to actually add and update Route 53 entries. So this was created in the previous step with Terraform. And this is all made possible by the last component called kubectl IAM, which allows us to add certain IAM roles to pods. So the alternative is to add IAM roles to the nodes in the cluster, but then if you go ahead and attach an IAM role, a permission to a specific node, all the pods on those nodes are going to have the same permissions, and you don't necessarily want that. You want to be able to say external DNS pod only has permission to access Route 53 API. My web app pod only has specific permission to access an S3 bucket, for instance, and similar. So once we created this values file, we can go ahead and add the FPCO repo to our local Helm installation. Go ahead and update that so it has all the information. And we can just invoke Helm install, the name of the chart that we're deploying, and we're going to specify the values file that we just created in the previous slide. So this allows us to create a cluster with all of these basic components that are hopefully going to increase the productivity of our team and the effectiveness. So hopefully I've shown the value of Kubernetes and how it abstracts over and automates some of the basic tasks that each software development team has. And most importantly, how it can make your team more productive and efficient. With that, I thank you for listening, and I open it up for questions.
Awesome. Thank you, Denny. One question that did come in a little bit earlier was when it comes to secrets management, is the preferred approach to use Helm to manage the secrets or to use kubectl directly to manage those?
So I don't have a preference for one or the other. There's a lot of charts that manage secrets via Helm, but you still have to set those secrets with the --set flag when deploying the thing. So it's going to template out the configuration map with those values, and it's going to store those in Kubernetes. We also use HashiCorp Vault for some of the secrets in our infrastructure, and that's also proven to be quite useful. So that's another option.
Cool, thank you. Another question was, can this be easily extended to Google Cloud instead of AWS?
Yes, so all of these examples that I've shown are transferable to Google Cloud if you exempt the part of the cluster creation at the beginning, because GCP offers a hosted Kubernetes cluster that you can let Google manage for you, but then you can go ahead and use all of the Helm charts and all of the other automation that we showed to deploy to that cluster.
Okay. Another question that came in, and I may be the one who ends up answering this, is Keter involved in any part? Denny, I'm not sure if you've ever worked with Keter before.
A little bit, but I don't think it's involved in any part here, no.
No, so Keter is something, it's actually a tool that I wrote, and it does predate my experience with Kubernetes. At this point, I do my own deployments on Kubernetes. I don't actually use Keter at this point. Keter does work fairly nicely if you have a single machine kind of setup, but as soon as you want to get high availability or horizontal scaling, it falls flat, which is why something like Kubernetes is the kind of approach that I take today.
Yeah.
Okay, there were a few other questions coming in. How are you dealing with pre-warming stack so that your first builds don't take forever on a fresh CI build node?
So that's an excellent question, and I sort of skipped over that part when building our images. So what we do is we either, in some cases, we use the GitLab native functionality for caching, but we wrote our own tool called cache-s3, which supports caching to S3, obviously, and it's sort of stack aware. So it's going to cache your .stack and .stack work directories to S3, and it has all these sort of intelligent understandings of, between branches, what sort of things to cache and what not. So that's what we use. So once we run the initial build, we're going to cache that, and on each of the subsequent builds on different branches, we're going to try and restore the cache for that specific branch, because the cache is per branch. But if the cache is non-existent, we're going to use the cache from the master branch, for instance, or from develop, depends on how you set it up. So hopefully that answers the question.
Okay, and there's a question if that tool is available in our GitHub repo. I think we could send out, probably on Twitter, we could send out a link to that tool afterwards, but it is an open source tool.
Yes, it is available under FPCO on GitHub, but yeah, sure, we can tweet it out.
Okay, let's see. Another question that came in. Is there a method for providing internal metrics, for example, Prometheus for Haskell app in Haskell and/or Yesod?
Yes, so we use Prometheus for all of our cluster/application monitoring metrics. So we use Prometheus operator, which sort of integrates directly into the cluster itself and makes it easier to deploy a Prometheus cluster on Kubernetes. It also automates some of the very important parts of adding new applications to your metric system, right? So it listens for new applications that show up given certain conditions, and if they have those conditions, it's going to automatically start ingesting metrics from them. And so this is like the previous points I mentioned, automatic SSL and automatic DNS entries, where a development team can totally sidestep the operation team and sort of integrate directly with the metric systems without any delay. So that's what we use. I can't remember the exact package we use on the Haskell end for exposing metrics directly to Prometheus, but I can look it up.
I think it's Y middleware Prometheus, but I know there were a few different ones, and I know we've had to change in the past. I'm not sure which is the most up-to-date one right now.
Yeah.
Cool. Another question that came in: will there be a link to your slides available?
Yeah, sure. We can make that happen.
Cool. And probably a bit outside of the scope, but can Ansible replace the Terraform parts you showed to us?
I imagine so, yes. I've used Ansible before for provisioning infrastructure like this, but I found it to be lacking, and the Terraform worked better in that regard. Ansible was more for provisioning things onto that infrastructure rather than provisioning the infrastructure itself. But yes, it is possible.
What do you think about Nix deploy and dal Nix for deployment, environment, and testing?
I don't have a lot of experience with deploying anything Nix related. I have recently reviewed a dal sort of a dal package that outputs Kubernetes YAML specs, but I've only looked at it very briefly. And haven't had any production experience with it. From my initial impression, it doesn't seem to provide much of a benefit over Helm in terms of templating, because most of the templating we have in our Helm charts isn't that, there's not much logic to it. They just, insert a value here. So I don't see the benefit of dal there.
Awesome. Does anyone else have any other questions? Awesome. Denny, thank you very much for a great presentation. Audience, everyone here, great questions, great interaction. Thank you very much. If you have any requests for topics for us to cover in the future, please do reach out to us and let us know. Twitter is a great way to do so, but any other venue will work as well. We will be continuing with these webinars on various topics related to Haskell and DevOps going into the future. Hope everyone has a good rest of the day, night, or wherever you happen to be in the world. Have a good one.
Thank you. Bye.